In this video, we'll cover limiting reactant problems using the example of a penny reacting with nitric acid. There are some new terms here, so let's define them. A limiting reactant is one of the reactants in a chemical reaction. It limits how much product can be formed because it runs out first. Theoretical yield is a calculation of how much product can be theoretically formed from the amounts of the reactants given in the problem. And percent yield relates how much product was actually formed in the lab to the theoretical yield that was calculated. The limiting reactant always refers to a reactant, and the theoretical yield always refers to a product. They are connected, though, because the limiting reactant limits the theoretical amount of product that can be formed. Limiting reactant problems can be recognized because amounts of two or more reactants are given. If two reactant amounts are given, then there are two calculations needed to figure out theoretical yield. The theoretical yield calculation uses the same problem-solving strategy as shown in the stoichiometry video. The link is above in case you want to check that out. The stoichiometry step is always required, and molar masses may or may not be needed depending on if grams is part of the problem. So let's see what this looks like. Let's say we were given 3 moles of nitrogen and enough hydrogen to react, according to this balanced chemical equation. We can see that we would be able to form 6 moles of NH3, which is supported by the stoichiometry calculation shown. If we were given 3 moles of hydrogen and enough nitrogen to react, then we could form 2 moles of NH3. And if we consider 3 moles of each reactant, we are limited to forming only 2 moles of NH3 because the hydrogen gets used up. It runs out first, whereas there is excess nitrogen. In this case, the hydrogen is the limiting reactant because it limits how much NH3 product can be formed. The theoretical yield is based on the amount of hydrogen. In our first example, we're given 0.04634 moles of copper and 0.0156 moles of nitric acid, and we are asked to calculate the theoretical yield of water in units of moles. So the first thing we do is take a look at the units given in the problem. Our reactants are both given in moles, and the product is given in moles, so we don't need a molar mass for any of them. Remember that with limiting reactant problems, we have to do the calculation twice. So calculation number 1 will be starting with copper, and calculation number 2 will start with nitric acid. So for calculation number 1, starting with what we're given, 0.04634 moles of copper. We set up our stoich step. Moles of copper will be in the denominator, so the units will cancel, and moles of water will be in the numerator. Grabbing the balancing coefficients to incorporate into our stoich step, we have 2 moles of water and 1 mole of copper. We'll cancel our units, moles of copper, and then check our sig figs. So our original value has 4 sig figs. Our stoich step is always exact. Those values are always exact. So our final calculation will have 4 sig figs. So doing the math, we have 0.04634 times 2 equals 0.09268 moles of water. Now, I'm not going to put a box around that yet because I don't know if that is my theoretical yield until I do calculation 2. So let's do that. So for calculation number 2, now we're starting with the nitric acid, 0.0156 moles of nitric acid. Setting up this stoich step, we'll have moles of nitric acid in the denominator, so the units will cancel, and moles of water in the numerator. Getting our balancing coefficients to use as our mole to mole ratio in the stoich step. We still have 2 moles of water, but now we have 4 moles of nitric acid. So we'll cancel our units and then check our sig figs. Here, our original value had 3 sig figs. Stoich is still exact, so this calculation will be rounded to 3 sig figs. And when we do the math, 0.0156 times 2 divided by 4, we get 0.00780 moles of water. So at this point, we've done the calculation beginning with each reactant. And now we have to look to see which reactant gives us the lower amount. And that is here. 0.00780 moles of water is the lower amount, and so this is our theoretical yield. So to answer the question, which reactant is the limiting reactant, we take our theoretical yield, we look backwards to see which reactant gave us that theoretical yield. And so it was nitric acid. So our limiting reactant, which again has to be a reactant, is nitric acid. To calculate the percent yield, we take the actual yield given in the problem, which was 0.00325 moles, divided by the theoretical yield that we just calculated, 0.00780 moles, times 100. Checking our sig figs, we have 3 sig figs for the actual yield, 3 sig figs for the theoretical yield. The 100 is exact, so our percent yield will be rounded to 3 sig figs. So when we do the math, 0.00325 divided by 0.00780 times 100, we get 41.7%. In our second example, we're given 9.83 times 10 to the negative 4 moles of copper and 4.68 times 10 to the negative 3 moles of nitric acid. And we are asked to calculate the theoretical yield of NO2 in units of grams. So calculation number 1 will start with copper, and calculation number 2 will start with nitric acid. Taking a look at the units presented in the problem, we're given moles of each reactant, but we are asked to calculate grams of NO2. So we'll need to calculate a molar mass for NO2, but not for copper or nitric acid. So let's go ahead and calculate that molar mass first. So we have 14.007 plus 2 times 15.999 rounded to 3 decimal places gives us 46.005 grams per mole for NO2. So to calculate the theoretical yield, we'll calculate moles of NO2 coming from each reactant. We'll determine which value is the theoretical yield, and then we'll apply the molar mass step to that value. You'll see how this works. So for calculation number 1, we start with what we're given, 9.83 times 10 to the negative 4 moles of copper. We'll set up our Stoich step. We need moles of copper in the denominator, so those units will cancel. That gives us moles of NO2 in the numerator. Getting the values from the balancing coefficients, we have 2 moles of NO2 and 1 mole of copper. We'll cancel our units and check our sig figs. We have 3 sig figs in our given value. Stoich is exact, so our calculated result will have 3 sig figs. When we do the math, 9.83 times 10 to the negative 4 times 2 gives us 1.97 times 10 to the negative 3, and that's moles of NO2. For calculation number 2, we'll do the same thing starting with nitric acid. So we start with 4.68 times 10 to the negative 3 moles of nitric acid. Our Stoich step will have moles of nitric acid in the denominator and moles of NO2 in the numerator. Getting the values for the mole to mole ratio, we still have 2 moles of NO2, but 4 moles of HNO3. We'll cancel the units and check our sig figs. We have 3 sig figs in the given value. Stoich is exact, so we'll round this calculated result to 3 sig figs. So doing the math, 4.68 times 10 to the negative 3 times 2 divided by 4 gives us 2.34 times 10 to the negative 3 moles of NO2. So now we compare the two values to see which one is lower, and that will be our theoretical yield in moles, and that is 1.97 times 10 to the negative 3 moles of NO2. We have one more step though. We need to apply the molar mass for NO2 to give us grams, so we'll do that right here. So for the molar mass of NO2, we need moles of NO2 in the denominator, grams of NO2 in the numerator. Remember, molar mass is always the mass of 1 mole. And then the grams are what we just calculated, 46.005 grams. We'll cancel the units. Checking our sig figs for the molar mass, we have 5 sig figs. The one is exact. So our final answer will be rounded to 3 sig figs coming from the theoretical yield in moles. When we do the math, 1.97 times 10 to the negative 3 times 46.005, we get 0.0906 grams of NO2. And that is the theoretical yield in the units requested in the problem, grams of NO2. To calculate the percent yield, we were given 0.0643 grams of NO2. That's the actual yield, divided by the theoretical yield that we just calculated, 0.0906 grams times 100. Remember that the units in the percent yield calculation have to be the same. So they can be moles and moles or grams and grams. But if one of the values has different units, then you need to convert. So the units are the same, and that way they will cancel. Both of these values have 3 sig figs, and the 100 is exact. So when we do the calculation, 0.0643 divided by 0.0906 times 100, rounded to 3 sig figs, we get 71.0%. In our final example, we start with 2.945 grams of copper and 4.91 grams of nitric acid. And we are asked to calculate the theoretical yield of copper 2 nitrate in units of grams. So we check the units given in the problem, grams of copper, grams of nitric acid, and we are asked to calculate grams of copper 2 nitrate, so we need molar masses for all three. The molar mass for copper we can just get from the periodic table, 63.546 grams per mole. For nitric acid, we need to calculate it. So we have 1.008 plus 14.007 plus 3 times 15.999. Rounded to 3 decimal places, that gives us 63.012 grams per mole. For copper 2 nitrate, we have 63.546 plus 2 times 14.007 plus 6 times 15.999. Also rounded to 3 decimal places, we get 187.554 grams per mole. Calculation number 1 will start with copper, and calculation number 2 will start with nitric acid. So for calculation number 1, we start with what we're given, which is 2.945 grams of copper. The next step is molar mass. So for the units to cancel, we need grams of copper in the denominator and moles of copper in the numerator. The molar mass is always the mass of 1 mole, and then the grams will be 63.546. We'll cancel our units and then apply the Stoich step. So moles of copper will be in the denominator, so that way our units will cancel, and moles of copper 2 nitrate will go in the numerator. We'll get the values from the balancing coefficients, and so we have 1 mole of copper 2 nitrate and 1 mole of copper. We'll cancel the units and then check our sig figs. We have 4 sig figs in our original value, 5 sig figs in molar mass. Stoich is exact. So our final result will be rounded to 4 sig figs. And when we do the math, 2.945 divided by 63.546, we get 0.04634 moles of copper 2 nitrate. For calculation number 2, we start with what we're given, 4.91 grams of nitric acid. Then we apply its molar mass. So grams of nitric acid will go in the denominator, moles of nitric acid in the numerator. Molar mass is always the mass of 1 mole. And then for grams, we have 63.012. We'll cancel the units and then apply our stoich step. So here, moles of nitric acid will go in the denominator. Moles of copper 2 nitrate will go in the numerator. Getting the values from the balanced equation, we have 1 for copper 2 nitrate and 4 for nitric acid. We'll cancel the units and then check our sig figs. We have 3 sig figs in the original value, 5 sig figs in the molar mass. Stoich is exact. And our final result will be rounded here to 3 sig figs. So doing the math, 4.91 divided by parentheses 63.012 times 4 parentheses gives us 0.0195 moles of copper 2 nitrate. Comparing the two values, the lower value will be our theoretical yield in moles, and it's this value, 0.0195. So we'll apply the molar mass conversion here to obtain this value in grams. So for the molar mass, we'll have moles of copper 2 nitrate in the denominator, so the units will cancel. Grams of copper 2 nitrate in the numerator. Molar mass is always the mass of 1 mole. And then for grams, we have 187.554. We'll cancel the units and then check our sig figs. We have 3 sig figs in the original value, the 0.0195. 6 sig figs in the molar mass, so our final result will be rounded to 3 sig figs. When we do the math, 0.0195 times 187.554, we get 3.66 grams of copper 2 nitrate, and that is our theoretical yield in units of grams. To get the limiting reactant, we now start with this value of theoretical yield, look backwards to the very beginning of this calculation to see which reactant gave us this theoretical yield. And when we do that, we see that the reactant was nitric acid. So nitric acid is the limiting reactant for this problem.